bienvenue à cette troisième soirée du colloque Wright pour la science, dont c'est déjà la 20e édition cette année. À nouveau, comme hier et avant-hier, vous êtes très nombreux, des centaines à être venus ici, écouter le conférencier de ce soir, aussi en ligne. Bienvenue à toutes et tous. Mon nom est Olivier Dessibourg, je suis journaliste scientifique et c'est moi qui ai le plaisir de vous accompagner durant toute cette semaine pour la modération de ces soirées. Comme chaque année, vous savez, on a le grand privilège d'accueillir ici à l'Université de Genève des orateurs de renom du monde entier. Cette année est un cru un peu particulier, puisque plus qu'un domaine, un seul domaine scientifique, les organisateurs ont choisi une thématique plus large, plus englobante, plus originale aussi, les 5 éléments. Une thématique qui remonte, comme vous le savez, à l'Antiquité. Tout commence en 460 avant Jésus-Christ, chez les Grecs, avec la théorisation des 4 éléments fondamentaux, la terre, l'eau, l'air et le feu, par le philosophe Empédocle, qui a par ailleurs lié ces 4 éléments aussi aux dieux grecs. Puis Aristote y va de son interprétation en y ajoutant la notion de 4 qualités liées à chacun de ces éléments, le chaud, le froid, le sec et l'humide. Le 5e élément vient un tout petit peu plus tard, et ce sera la vie. Avant que d'autres domaines ne s'emparent de ces idées, de la cosmologie à la médecine, en passant par l'astrologie, la diététique et la biologie. Alors cette allégorie de la constitution de toute substance dans l'univers nous servira plus de référence que de cadre formel ce soir, comme d'ailleurs tous les soirs de cette semaine, pour parler des géosciences, de différents domaines des géosciences et de découvrir les recherches de 5 spécialistes de renom des sciences de la Terre. Comme vous le savez maintenant, cette soirée se déroulera en 2 parties. La première partie, une conférence par l'invité de ce soir, et une deuxième partie de questions-réponses auxquelles vous êtes cordialement invités à participer en posant vos questions ici directement dans la salle, également en ligne, et vos questions seront retransmises par quelqu'un au conférencier de ce soir, et ceci autant en français qu'en anglais, car à l'entrée vous avez dû recevoir un casque de traduction simultanée. Ce soir, nous avons l'immense plaisir de partir sur les océans, dans les océans plutôt, avec un expert mondial du domaine, Ilker Fer, qui est professeur à l'Institut de géophysique de l'Université de Bergen, en Norvège. Et pour le présenter, ainsi que ses recherches, je passe immédiatement la parole à Thierry Courvoisier, qui est professeur émérite d'astrophysique à l'Université de Genève et président de la Fondation Wright. Thierry.
Merci. L'université étant dépourvue, probablement pour de bonnes raisons, d'un département d'océanographie, il revient à un astrophysicien avec quelques connexions maritimes de présenter le professeur Ilker Fer ce soir. Les océans sont loin d'être des masses d'eau plus ou moins inertes, traversées de courants à géométrie simple. Souvent, le navigateur se trouve surpris par des mouvements contraires à ce que la sagesse populaire imagine. Le Gulf Stream, par exemple, n'est pas un fleuve linéaire au milieu de l'Atlantique, mais un complexe de mouvements et de contre-mouvements. Comprendre la nature de ces mouvements est essentiel pour connaître la part des océans dans la physique de toute la planète. C'est le centre de l'activité du professeur Ilker Fer. Ilker Fer est d'origine turque. Il est maintenant professeur à Bergen en Norvège. C'est un physicien spécialisé dans les zones polaires des océans, des zones dans lesquelles des eaux froides et denses coulent vers le fond, entraînant ainsi toute la circulation océanique. Mais il ne faut pas croire que les océans ont le monopole de la circulation d'eau de différentes propriétés physiques. Le Léman est aussi le théâtre de tels mouvements. Ceci est tellement vrai que c'est au bord du Léman et en l'étudiant que le professeur Fer a obtenu son doctorat en sciences en 2001 sous la direction du professeur Ulrich Lehmann de l'EPFL, avec un travail qui est devenu une référence dans le domaine. Ilker fait une carrière brillante, en mouillant littéralement sa chemise dans des expéditions arctiques en mer de Barents, voire en se laissant dériver sur la glace polaire pendant l'hiver. C'est une recherche profondément ancrée dans ce que la nature a de plus rude à nous proposer. Et il est indispensable de se soumettre à ces rigueurs pour avoir accès à la connaissance des océans. Le chercheur traduit ensuite les réalités qu'il est amené à vivre durement et à mesurer, en savoir. Ilker est ainsi l'auteur de nombreux articles de recherche richement cités et titulaire du prestigieux prix Georg Wüst pour son travail sur la turbulence, les mélanges et la formation d'eau dense aux hautes latitudes. Il est membre de l'Académie norvégienne de recherche polaire et éditeur de journaux de premier plan en Europe et en Amérique. Les universités norvégiennes sont un riche terreau scientifique dans lequel j'ai eu le très grand plaisir de partager de nombreux moments fructueux. Je suis très heureux du contact de notre université avec celle de Bergen, qui illustre la présence du professeur Fer ici ce soir. Merci, Ilker, d'être avec nous ce soir. Nous nous réjouissons de t'entendre et la parole est à toi.
Thank you. Well, the third element, the water, I will be talking about the ocean representing the water. It's a pleasure for me to stand in front of you, talk about the ocean in this prestigious venue offered by the Wright Foundation. And I'd like to extend my thanks for the organizer for inviting me. I will talk about the turbulent ocean, technological frontiers, new paradigms, and the emerging Arctic in particular. So I'm a physical oceanographer, so that's all about the ocean physics, how the waters move about, and how we, through interaction with the atmosphere, with forcing from the atmosphere, how we modify the properties of water. Our planet is covered more than 70% water, and the ocean offers more than 95% of the Earth's living space. So it's very natural to call this planet ocean, as many refer to. The ocean has been going through many changes recently, in the recent decades. A manifestation of that is the global surface temperature. This is the temperature anomalies relative to a 30-year baseline period from 1951 to 1980, showing the warming in the Earth's surface. Red colors are the warming, blue colors are the cooling. You can see that it's dominated by red colors and increasingly so in the recent years. And the last decades, the nature has been sending us messages again and again that something is happening. So each year has been a new record. I think 2021 tied up with 2018 as the 6th warmest in the last decade for the global average ocean temperature, global surface temperature. So ocean provides our livelihoods. It provides us oxygen, food, medicine, and besides that, it also sucks up carbon from the atmosphere. It takes up the heat and maintains that, absorbs that, and keeps that, thereby mitigating the pace of the climate change. So it's regulating the negative effects of the climate change in our planet system. So ocean regulates our climate by storing heat and carbon. Heat because the heat capacity of ocean is large. Like 1 meter of ocean, it's corresponding to like 30 kilometers of atmosphere. So with that, the ocean takes the heat and maintains it long time in the deep ocean. I think about 90% of the excess heat induced by human activity since the Industrial Revolution was taken up by ocean. Carbon dioxide, about 1/3 of that was taken up. So ocean is doing us a huge service, but there's a but to it, at expense of ocean warming, acidification, deoxygenation, sea level rises, melting ice caps, thawing permafrost, and more. Sea level rise, it's a global challenge and particularly problematic for coastal nations, island nations, coastal communities, and also for well-developed economies. Since the start of the observational period, starting from tide gauges, continuing with the satellite remote sensing measurements, we find that the global sea level has increased by 22 centimeters since late 1800s. And this is continuing to increase at an accelerating rate. So at the 90s, the trend was 3.5 millimeters per year. In the last decade, it's 4.6 millimeters per year. In other words, in 12 years or so, we'll add additional 5 centimeters to the sea level rise. So that happens because of at least 2 reasons. One is the ocean warming. If you warm water, the molecules expand, occupy more volume. The other is the mass influx from melting land ice, glaciers, and ice sheets on Greenland and Antarctica. Of course, this has huge consequences for our climate system and also locally. Here's a nice picture from Bergen, where we live. This is from Bryggen, looking to the fish market. Bryggen is a UNESCO National Heritage region, and this time after a storm surge, it's underwater. So the ice loss from Greenland is huge. Along the parameters, we are talking about large masses lost, and that adds into the water level. If the entire ice sheet of Greenland had melted, it corresponds to about 7 meters. The melting reason, okay, we have the atmosphere, but also the warm waters coming to the marine terminating glaciers. Interaction and turbulent interaction leads to melting of those. I don't want to tell you how many meters additional sea level you get if you melt whole Antarctica. That's a lot. But Antarctica is melting primarily on the Amundsen Sea, like the Pine Island Glacier. You see that on the map, on the red spot there, lots of mass loss happening. Oceans are all interconnected. We can see that nicely on this Spillhouse projection of the ocean. Different basins of the Arctic, Atlantic, Indian, Pacific Oceans around the Antarctica, they are all interconnected with the ocean circulation, moving about the waters and heat and carbon and dissolved gases. You can see you can't see the 3D circulation or 3-dimensional nature of it. Maybe in the next slide we can. So that's the idealized representation of the ocean circulation in 3 dimensions. The ocean currents are represented by these arrows. These are the slow-moving, wind-driven typically currents. It's called the thermohaline circulation due to the changes in temperature for thermo and salinity, haline, which together determines the density of the seawater. You can see the Gulf Stream coming to the northern latitudes and taking around, and this warm water is responsible for the relatively warm climate in the northern Europe, and it keeps the waters around Iceland and Greenland ice-free year-round. So this water, as it travels around the basin there, it interacts with the atmosphere, loses lots of heat, gets denser, and sinks to the bottom. When it's at the bottom, these dense waters then circulate southward. That's the global overturning circulation. So the vertical structure is of huge importance, although the aspect ratio of the ocean is like a sheet of paper. So these waters circulate to the equatorial regions, and there they have to upwell. They have to rise to the surface again. So one water parcel starting from the surface, sinking down, and getting back to the surface, it takes about 1,000 years. But that's how we can mitigate the climate change in a way, storing the carbon and the heat in the ocean. If you go farther south, at about 60 degrees south, the waters around Antarctica, there's no obstacle for the motion of the ocean. So the currents can travel all the way around. And this allows the waters to upwell in the Pacific Ocean and the Indian Ocean. Another important aspect of the Antarctic regions is the dense water production. The very dense waters produced in the Weddell Sea and in different regions sink all the way to the abyss of the ocean and start filling from there. Well, the ocean circulation is not so simple as like straight lines and arrows. As Thierry mentioned, the Gulf Stream, all this variability. So there are There are lots of activity, like the swirls of motion, the weather of the ocean, that is not represented in this picture. So we have to understand those processes because our understanding of the climate, the climate comes from our ability to model these processes. And the way we do that is we believe in the laws of physics, thermodynamics. We have those equations and we grid the ocean and we apply the equations and solve on supercomputers. So each of these boxes are 1/10 of a degree longitude latitude. That's about 10 kilometers. So we are talking about a 10-kilometer box on which you have no information what's inside. All the weather of the ocean and the turbulence that I'll come back later happens within. So we have to understand those properly so we can represent them in such models when we solve the equations. That's an example of what's going on when you model at this coarse resolution. That's fairly high resolution for a global model. You can see the Gulf Stream meandering and the swirling eddies, the warm waters of coming from the Florida current, and then interacting with the cold waters from the Labrador current. All this variability. So there's a unit for the volume flow in oceanography. That's called 1 Sverdrup. That's 1 million cubic centimeters per second. That's named after the famous Norwegian oceanographer Harald Sverdrup, who was the former director of the Scripps Institution of Oceanography. So the average flow rate of this current is about 30 to 50 Sverdrups. 1 Sverdrup equals to all rivers combined flowing out to oceans, about 1 Sverdrup. As we approach the equator, the size of the swirls get larger because of the planetary constraints. But the pulsing and all the action going on in this simulation shows you how dynamic the ocean is. It took quite a long time to get there. We didn't know the ocean was so dynamic. Back in the day, only one human life ago, they were thinking the ocean was quite stagnant at deep waters. It's quite quiescent, nothing going on. So that's the Challenger in the Southern Ocean, a 4-year expedition in 1872 that laid the foundations for oceanography, collecting data on ocean currents, temperature, geology, and chemistry. So still then, expeditions continued, but it was to the stage that if you deploy your device at the same location again, it was considered like a waste of money or resources. You don't want to collect more data, nothing going on. And it was all simplified. And ships have been the main means of collecting data for many years to come. But observations were mainly coarse, typically multiple 10-kilometer separation between the station. So these lacked the complex interactions of the ocean we just looked at. So if you look at the global scale, you have the large-scale currents. These become unstable. They shed eddies, swirls, expel those, and then they interact with each other. These eddies can be between 10, 100-kilometer scale. And interacting through them, they lead to mesoscale phenomena, like filaments, say from kilometer scale to hundreds of meter scale. And then farther, you go down to submesoscale and then small-scale turbulence at the order centimeters. So you have to resolve all these interactions, all this spectrum of scales to properly represent what's going on in the ocean. In the recent decades, there's been huge developments. So typically, research vessels equipped with modern instrumentation, devices to measure the structure, temperature, salinity structure of the ocean, and the horizontal currents have been used to enhance our knowledge of the ocean. Satellite remote sensing. Satellites equipped with active or passive sensors like radiometers or radar altimeters, they allowed us to map the ocean surface for sea surface temperature, the topography of the ocean. All this activity, ocean weather, leads to sea surface variability that you can detect from remote sensing. or the sea ice extent, or the ocean color that represents the biology. Then the invent of the microstructure profilers, these are instruments specifically designed to measure ocean turbulence, have opened up a new perspective where we started collecting data on ocean turbulence. Maybe most recently, the ocean robots have made huge progress. They have become a mature technology. Some are propelled assets like the autonomous underwater vehicle, like this one from Kongsberg, the red unit in the middle. Or they can be ocean gliders, gliding in the water column up and down with their own buoyancy, collecting data throughout. Or they can be an Argo float. An Argo float is a robotic device. It's designed to be expandable. After 5 years or so, when battery dies, it's over. So it's ballasted for a target depth of, say, 1,000 meters. You deploy this device, it sinks to 1,000 meters, not collecting any data, just drifting there for 10 days. Then, using its buoyancy pump, it sinks to about 2,000 or 6,000 meters. On the way up, it collects data on essential ocean variables. It can be temperature, salinity, or even biogeochemistry, like dissolved oxygen. And between this 10 days period, between the surfacing locations, we can get an estimate of the surface current, of the deep current. Argo is an international program contributing to the global ocean observing system. Now, at a given month, we have more than 3,000 operational Argo floats, giving this exemplary coverage of the world ocean, providing maybe 400 profiles a day. With this information, then, we can accurately calculate the heat content of the ocean. We have the data we need to do that. An ocean glider, in contrast to a float, it just glides with its buoyancy up and down in a sawtooth pattern. It's a remotely piloted asset. You can give it some coordinates. When the instrument comes to the surface, you can send the new waypoint, and you download the data. It's accessible in your computer right away. They can live for months to a year-long missions, providing data no matter what weather condition or sea state. That's one big advantage of the ocean gliders. Another advantage is that this data being sent through satellite, it's then harvested by the operational centers. They can use this data, assimilate in their weather forecasting models on the fly. Every day they can adjust their models with proper data coming out. Argo floats, ocean gliders, contributes to a better operational system, better weather forecasts. So with all these tools we have available, we can map the heat content in the ocean. This is the heat content graph for the Earth system, split into atmosphere, ice and ground, and ocean. Ocean by far absorbed the most heat, by 90% since 1960. The unit here is a zeta joule. That's a joule with 21 zeros after. So it's lots of heat we are talking about. But if you look at the vertical distribution, just take the ocean heat and look how it is in the vertical. The upper 300 meters is only 40% of the total heat content. So amazingly, there's lots of heat going on all the way to the ocean bottom. We can understand how all this radiation is absorbed in the upper ocean. That's where the heat comes in, that will be there. But how do you bring it all the way down to 6,000 meters? So the eddies we looked at, the ocean weather, that distributes heat laterally. But vertical mixing, turbulence, it distributes vertically. So to get these right, you have to get the turbulent mixing in the ocean properly. Just for your reference, this large number of energy in the heat budget, it corresponds to about 60 watts light bulb heating 100 Olympic swimming pools, if my calculation is correct. So we are talking about a very small energy here, but has huge consequences like the global warming, the climate change. So we have to get this small number right. turbulent mixing redistributes the heat vertically. And that will be the main topic for the remainder of my talk. So you say, what is turbulence? You are used to turbulence from normal day, every day. In Steve's talk, we had this outbursts of eruptions of volcano. It's buoyant plumes rising up, and you can have a cigarette smoke getting mixed with the ambient. Lots of examples of turbulence. So if you don't have turbulence, a patch of red water here in this white environment will diffuse by itself, by molecular diffusion. It will take some time. But if you stir it, if you put energy into it, like you put sugar in your tea and then you stir it with a spoon, it will mix much quicker. That's the turbulent mixing at rates much larger than the molecular rates. If you don't supply your energy into that, it will die out. But the ocean needs energy all the time because you have to maintain the circulation, and turbulence is at the heart of this circulation. So what is providing this energy? Turbulent mixing in the ocean is fueled by wind and tides. So you can see the surface waves at the ocean breaking, generating turbulence is visible to you. Just like that, in the interior ocean, we have waves. Ocean is layered, stratified. Between each layer, you can have waves. And they are much larger, tens of meters in amplitude, and much slower in time scale, hours. But when they break, they are turbulent. They fuel the energy. So you can generate these waves from top by the winds, or you can generate them by tides sloshing back and forth over topography. In Lake Geneva here, we don't have tides. But tides is an important component in the global ocean turbulence budget. So these energy scales are the scales by interacting through different wave packets, cascade down to smaller scales, and finally to turbulent mixing at centimeter scale. So for the rest of my talk, I'll give you some examples from some of our research in the Norwegian Sea, and then higher north in the Arctic Ocean. So Nordic seas is the common name for the Greenland, Norwegian, and Iceland Sea. It's the heart of the global overturning circulation, this large-scale ocean circulation. So you see two branches of warm water, the North Atlantic current, carrying warm waters into our latitudes in Norway. So that's responsible for the warm climate over there. You see one going over the Moon Ridge. So that's the mid-Atlantic ridge that's steering the currents. Another arm following the slope of Norway. And these carry on into the Arctic Ocean. In Fram Strait, between Greenland and Svalbard on the north, they make a turn and circulate back along Greenland. So in this circulation, they lose lots of heat. They get denser and sink to deeper levels. And they flow out to be this loop, the northern limb of this overturning circulation. The channels like between Faroes and Shetland and the Denmark Strait between Iceland and Greenland are the main passages for these deep waters to come to North Atlantic. In the Norwegian Sea, a Lofoten Basin sticks out, it stands out. It's the basin between the two branches of this Atlantic water current. If you look at the heat content, it's warm. The heat is distributed laterally and also vertically. Heat content is nothing but integrated temperature. If you look at the surface topography from satellite data, altimetry data, we also see that it's highly energetic. Lots of eddies and swirls going around. So this energy, which we call the eddy kinetic energy, averaged over some time, looks like this. You have like a red spot in the middle of the basin. We've discovered that that's the Lofoten Basin eddy. That's a vortex, semi-permanent. It's always there. So the boundary current gets unstable and sheds those swirls of vortices going into the basin and collected in the basin within this vortex. This is important for fisheries. You have lots of blooms. This is an example from the satellite image showing the chlorophyll A distribution. And you have lots of small mesoscale activity, which you can see in a parameter that shows the swirling strength of the water column relative to Earth's rotation. It's lots of structure there. So we had a project done. We wanted to study this vortex in the basin and understand the dynamics of that. So what is that? You say spaghetti looking like lines with some sticks going on. These are transects, or the missions, from 4 gliders, ocean gliders, collecting data for us. They've been out there collecting thousands of profiles for 2 years, working its way through the basin into this vortex, spiraling in and out, and lots of ensembles you put together and get a nice picture of the dynamics, what's going on in that eddy. And also over the Moon Ridge at the front between cold Greenland waters and the warm Norwegian sea waters. What's going on there? The good thing about this is that you get data no matter what sea state or weather conditions. When you're out there with a research vessel, you have to interrupt the sampling because it's bad weather. Like in here, that's from a cruise in March, then we couldn't collect any data. So there comes the strength of the ocean robots, like those gliders that collect data and help us to sample no matter what condition. So we didn't only have gliders, but we also had some floats that we could acoustically track. That you deploy something ballasted for certain depth, say 500 meters, and you can track that by acoustic triangulation where it is. So we had a bunch of those. This is a movie showing all the assets put together, synthesizing that to show you the coherence of this vortex, what's going on. You can see the ship coming in and out, the floats being trapped at this virtual boundary of the vortex, and the glider coming in and out of this vortex, spiraling in and out occasionally. So you can see that most of those floats are trapped inside this eddy of this vortex, just wobbling around in the basin. The diameter is about 30 kilometers, that circle over there. Some of the floats that are relatively shallow, like 250 meters, they escape. Because near the surface layer, you can remove some of the dynamical constraints, barriers induced by the rotational effects through air-sea interaction. So it was crucial for us to collect all this detailed data to understand the physics of what's going on here. But it's a very coherent structure lasting for a long time. So then you have your ship going into the vortex. So we occupy different stations starting from the outside of the eddy, collecting profiles and putting those together. That gives you a snapshot of across this vortex. Because it's a circular structure, it's enough to cover just half of this. You can see that. So that's the temperature we are looking at, measured by this frame equipped with devices to measure the temperature, salinity, and the ocean currents. You see, say 1,000 meters depth, away from the core, away from the center of the vortex, there are cold waters, blue colors. In the core, it's trapped warm waters, all the way down to 1,200 meters. It's the same for the salinity. This is the salinity diagram, so you see that the red colors are higher numbers for higher values for the salinity. Now, those who claim that the ocean was quiet at depth, nothing going on, look at that one. So that's the swirl velocity of this vortex. We are looking at in meters per second. It's like a river flow, up to 1 meter per second, at 1,000 meters depth. That's at the base of this vortex. You have so large currents and strong shear. It's highly turbulent. So that has consequences for the life cycle of this vortex and also for the biology. We can measure the turbulence with this dedicated device. It measures all the small-scale fluctuations. If you look at this 1,200 meter region, at the base of the eddy, there are very large numbers of a parameter called dissipation rate, epsilon. That's a proxy for the turbulence intensity. And the scale is logarithmic. Each jump is factor of 10 times, 100 times larger than the background levels. For reference, the numbers at this red band, they are comparable to surface turbulence in under strong wind conditions. I think it was a cool discovery to get all this. So I'd like to move farther north into Arctic Ocean. Arctic is the canary in a coal mine. Why is that? Because it's the polar amplification, the Arctic amplification. The warming rates in the Arctic Ocean is at least twice as large as the global average. Here you see the surface temperature reaching up to 4 degrees in the Arctic regions. That's because of mainly the albedo effect, the reflectivity effect, the Arctic Ocean. By the way, Arctic Ocean is an ocean. So it's not land, it's, you have 4,000 meters of water under sea ice. Sea ice can be a few meters thick, and it's under constant motion. It's just moving with the tides, with the currents, with winds. So if you remove the ice, then you expose the surface, its darker surface, the water, it will absorb more heat from the radiation. So if you remove sea ice, then you let the ocean absorb more heat. As a result of that, or chicken and the egg problem, the Arctic sea ice volume is shrinking. So this animation showing the huge changes in the sea ice volume. Not only the horizontal extent is shrinking, but also the thickness. Multi-year ice, that's sea ice that survived at least one summer, they are very limited now. You used to have 5-year-old ice. I think it's less than 95% has disappeared. So where does this heat come to? What's the reason of this melting of sea ice? Of course, atmosphere is the huge player, but we can't ignore the ocean. I'd like to advocate, maybe hopefully convince you that the ocean is important and ocean turbulence is very important. Heat comes to the Arctic Ocean from 2 gateways. One is the Fram Strait and the Barents Sea, this red Atlantic water inflow coming in. And another gateway is Bering Strait from the Pacific Ocean. This heat then circulates in the Arctic Ocean. And if there is sufficient heat in the Arctic Ocean to melt the sea ice several times over, but these warm waters are subsurface. They are submerged under very cold waters. But changes are happening in the Arctic. With the changing Arctic, I can mention the Atlantification. That's a word for that Atlantic water reaches higher up, and there's more of that in the Arctic. There's declining sea ice, leading to stronger seasonal cycle. Sea ice, you have a summer minimum and a winter maximum. That's the seasonal cycle. It's strengthened. That can lead to more wind energy input from the winds that can fuel more turbulence and more vertical mixing. So this loss of sea ice, what you need is only 1 watts per square meter perturbation to account for that. 1 watts per square meter is a very small number. That's what's happening now, that we are losing all this sea ice. Atmosphere can account for, of course, much, but the ocean has a zoo of processes that can account for that. For example, this warm Atlantic water, the red parts of this cartoon, it goes over very tidal mixing regions. Then you can extract this heat all the way to the sea ice. Then the eddies stir horizontally and distribute this heat. You have all the internal wave field in the interior that alone accounts for maybe 1 watt per square meter background mixing. And also you have a peculiar structure of the Arctic Ocean, which results in this staircases where the temperature is increasing like a staircase. That's a particular effect that can account for like 1 watt per square meter. If you look at the Arctic Ocean profile, so you see the red temperature, black the salinity under sea ice. Freezing point temperatures down to 100 meters. That's in the central Arctic Ocean, okay? And even though it's at freezing point, starting at about 50-ish meters, you have this gradient in salinity. That's a stratification that caps this warm water from below. So you have the cold mixed layer and strong salinity stratification, and you have the warm Atlantic water. If you have the ability to mix this heat upward, then you can melt the ice. That's a dangerous scenario, but it can happen if you remove the sea ice, so you bring in more wind energy that can fuel turbulence. But this cold layer with salinity, called the cold halocline layer, kind of caps this. There's a nice picture of a polar bear swimming in open waters, but I'm sure she appreciates more living on sea ice. This was from a cruise we did this summer. So with this motivation, what's the role of the Arctic Ocean heat for the sea ice cover? I staged several experiments, starting with the International Polar Year in 2007. Then we went to this ice camp near the North Pole called Borneo, and there make a hole in the ice. Again, you have 4,000 meters of water, ocean underneath, over 2 meters thick ice. So we deployed our instruments and collected data on ocean turbulence, temperature, salinity, and currents. We learned a lot from those. It's similar temperature salinity structure on the left panel here. The diagrams are technical because it's just taken from scientific research papers. Ignore that. The black shaded curve is the dissipation rate of turbulence. That's the turbulent proxy we talked about. The larger numbers, the more turbulence. So we see those background mixing at the bottom below 200 meters. That's because of internal wave breaking. But what we see at the top, reaching as deep as 100 meters, is the energetic turbulence from wind-forced internal waves. So we managed to describe that thanks to this data we were able to collect. We also found out that this stratification of salinity in the upper layer makes it impossible to mix across the barrier. But again, if you energize the internal wave field, you can remove that. So that can be a bad feedback for the sea ice. From the Pacific side, okay, we were at the Central Ocean, Arctic. Now let's go to the Pacific. Our colleagues from the Scripps, they identified those heat bombs destroying the Arctic sea ice. So these warm, salty pockets of water, they are expelled from the boundary current, the jets along the Alaskan coast. And this warm water can dive underneath the sea ice. And as it does so, it mixes with the ambient water and the waters from below, drawing in nutrients, which is essential for the biology. And then these start swirling and trap the waters, trap the heat for many months, maybe years, and they propagate into the interior of the ocean, of the Arctic Ocean. So this is a means by which you can extract heat from a boundary current and push it all the way to the central or Arctic and remove the heat, remove the sea ice. What's happening on the Atlantic side? So Atlantic side is more energetic. There's more heat, more action. We didn't call it heat bombs yet, but it's lots more going on in terms of heat transfer. So in 2015, we had this Norwegian young sea ice expedition where we froze a research vessel into sea ice and drifted with sea ice. Everybody jumped on ice and collect data. North of Svalbard, drifting with the ocean currents, with the sea ice, again and again from winter time to summertime. We collected lots of data. We synthesized all that together. What we learned was if the Atlantic water, that's the subsurface warm water, is close to sea ice, if that's close to topography where tides are acting energetically, and if you have storm events, you can extract as much as 100 watts per square meter to melt sea ice. Remember, you only needed 1 watt per square meter, so such events can have importance on the large scale. Another thing we learned, we also had deployed some instruments just under the sea ice, the boundary layer below the sea ice, collecting data, also in wintertime. So in Arctic winter, it's all dark. There's no radiation forcing. So only heat source is the ocean. So we thought if we can quantify the contribution of ocean in winter, that's it. We know how much it's coming up. So look at the black and gray kind of part of this histogram of heat fluxes, going from 0 to 15 watts per square meter. So in winter time, in quiet conditions, calm, no winds, no nothing, you get about 1 watts per square meter oceanic heat flux to ice. And in storms, that's doubled. So that's a huge input during winter time, and there's no other source of heat. A major undertaking recently was this MOSAIC, multidisciplinary drifting observatory for the study of Arctic climate, using the research icebreaker Polarstern, the German icebreaker, as a platform. So this was there for 1 year, collecting data for entire annual cycle. The plan was then drift from the Laptev Sea, high north, through the Fram Strait out. And the drift was faster than planned, so the vessel came out of sea ice in June, July, and then we had to go back to north, near North Pole, and start drifting again. But different disciplines, atmosphere, cryosphere, sea ice, ocean, collected huge amounts of data, ecosystem biology, biogeochemistry. So there are workshops, conferences, just going through this data. I'd like to emphasize or highlight just one thing I was involved in. That was, I can't go through this whole MOSAIC expedition, but we had a specially designed instrument that's an Upriser microstructure profiler. So that's a buoyant instrument that will rise, that wants to float. So we forced this instrument by weight down to 50, 60 meters, and then we release the weight, and that will rise with its buoyancy. By doing so, it collects data until it hits the ice. We were not afraid of hitting the ice because it has those protections on the sensors. So again and again, we profiled with this. So resolving the turbulent structure under drifting sea ice. So the sea ice is moving a lot. Along this drift of the MOSAIC frozen into the sea ice. We had about 200 profiles in different conditions, different basins, different wind, drift, strength, and also in leads. And also maybe close to ridges. So the sea ice is not flat. All the pressure, the ice is in constant motion. All this pressure acts to generate ridges, maybe a few meters tall at the surface, but that's the tip of the iceberg. Below that, you have maybe 8, 10 meters of a keel. So that means a lot for the boundary layer under ice, how much you can extract heat from the warm layer below. So we did lots of analysis. So you see here, by the way, the different images of how it looks like in June, and later in September when you have lots of melt ponds at this ice surface. So we went out with a Zodiac, for example, collected data from holes in the ice, and lots of details. This is a picture showing the elevation of ice at the surface and the draft, what the ice thickness is below. You can see the red colors reaching 8 meters. And for those who haven't seen a sea ice before, it's not flat, it looks like this. And you can have lots of melt ponds, the melt snow, making life difficult to navigate from point A to point B. Anyways, these are very exciting for me, so probably not for you. But what we learned on the pack ice is no cracks, nothing, drifting pack ice. The turbulence in the upper 20 meter increased markedly for high drift speeds because you drag waters, you have friction, you have turbulence generation in the upper 20 meters. In leads, so leads are the cracks between ice flows. In leads, you have strong interaction, large interaction with the atmosphere. So you can lose heat, or wind can force turbulence. The upper 2 meters in the leads was 10 times more energetic than in thin ice, compared to thin ice. So this kind of data allowed us to categorize a bit more, understand a bit more. It's still early days, baby steps, but we are getting there, and such technology is allowing us to collect good data. Ridge keels, 5-8 meters thick extension of the sea ice was generating lots of turbulence. Final process, so I'm trying to give you some different flavors of what's going on, like mixing processes in the Arctic Ocean. This is the final one that goes into the parameters, what's going on, and that's about the tides. Tides, when they work on topography, like I mentioned before, they can generate some phenomena that can lead to turbulent mixing. The story in the Arctic Ocean is a bit complicated. It's not linear. We find out recently, using some detailed data, that the pathway of energy from tides to turbulent mixing was highly nonlinear. That means that's it's difficult. So there's a bunch of parameters I'm not going to explain, but if you look at the map, you see that there are some bright green colors where the tidal velocity maximum heading on slope onto the topography can be as large as 1 meter per second. That has a large significance for the internal tide-induced mixing. So what's happening here, if you imagine two layers, one the surface, the other one is the thermocline or the pycnocline, where you have the stratification, and you have topography. So when the tide pushes the water over the sill, over this topography, it depresses the this surface, and like a lee wave, what we call. And so that wave wants to propagate, wants to leave that site toward where it was generated. But the ocean current, the tidal current, is so strong that it traps it. The wave can't go anywhere, so it's trapped. But during slack tide, when the tide relaxes, the wave is free to propagate, but it's not trapped anymore. And with the flood tide away from the topography, then it's getting steeper, and the pockets of, or trains of waves develop which are steep and they can break and lead to turbulence. That's all textbook material, but we actually observe that. North of Svalbard, one transect you are looking at here, starting from 100 kilometers going in towards shore. We occupy these stations collecting turbulence data. Okay, the colors here are a representation of turbulence. Bright red is very turbulent. At this 300-meter isobat depth, the entire water column is turbulent. Large numbers, 10 to the minus 6, that's under a storm level of turbulence. The inset there, it shows you the crests of waves that are seen by the satellite. SAR imagery. Because internal waves have a roughness signature at the surface, you can detect those with satellite images. So at this star, we put there by the 300 meters depth, you can see a bunch of small waves being generated and propagating. So we said, okay, let's go there and be there for 24 hours, repeatedly collecting data. The team was not happy, but we collected a nice time series of turbulence profiles showing this entire 300-meter, it's, I don't know how long the Eiffel Tower is, but it's tall. The entire water column is turbulent and consistent with this textbook theory of what may be going on. And we claim that that's quite common in the Arctic Ocean. So it's a new paradigm that can, or showing the routes, pathway of energy to turbulent mixing. It can be as large as 100 watts per square meter. You probably now forgot how much we needed, but on average we need 1 watt per square meter to melt the sea ice. So I probably spoke like 2 hours, I don't know, but this is my final slide. So our ability to predict what's going on has increased substantially. We are learning a lot with this new technology. And we live in exciting times. It's exciting to have all this technology that we can collect good data and make major advances. With this, I'd like to thank you all for your patience, and I'd like to round up with a quote from Doug Webb, the founder of the Teledyne Web Research and inventor of the Slocum a glider that work hard, have fun, and change the world.
Thank you, Ilker Fer. Please take a seat. Comme vous le savez, c'est la richesse de ce colloque d'avoir plusieurs conférenciers durant toute la semaine. Des conférenciers, pour cette fois, qu'on a décidé d'inviter en nombre sur scène pour discuter, pour élargir la discussion. J'ai donc le plaisir d'inviter ce soir avec nous Kim Prather de l'Université de Californie à San Diego, Friedhelm von Blankenburg et Nick Lane qui est là avec nous. Merci de nous rejoindre. Take a seat. So I'll switch to English and start maybe with a 5-minute discussion. Then I'll open the floor to questions. And maybe before we start with the other guests, 2 precision questions to you, Ilker. The first is related to your last slide, actually. We saw how detailed you go in the observation of the ocean. But at the same time, the ocean is so big and so complex that I'd like to ask you, on a scale of 0 to 10, how high would you rate your good understanding of what we know or don't know of the ocean, and how to go higher?
Yeah, I think it's key to increase our process understanding.
Between 0 and 10?
How high we need to go? 7 is good enough, I guess.
7? Okay.
But I think it's key to emphasize that these process studies, you study the process, you learn from that, and then that can be applicable globally or where it happens. So that's the goal, to do process studies. You don't need to do it everywhere, but you do that and learn from it and improve your understanding of it. We have to increase that maybe to 10, just the process.
So you say you will learn. I'd like to ask you, our 3 guests, how far is what you've just listened to now useful to your field of competence, to your research on the ground? Maybe starting with you, Friedhelm. We've heard from you on Monday that you're studying this thermostat that is governed, if I can say that, by the CO2 emitted by the volcanoes and also absorbed by the rocks. But how far are the oceans interesting or useful for you? How is this research, how could this research be useful for your research as well?
Well, first of all, I used to do related studies myself, but like a few years ago because the isotopes that I use, we can use those just in the same way to track ocean circulation, both in the present and now. So the topic is a bit familiar to me in that regard. However, but your question, how does the regulation of Earth's climate, how is the ocean linked to it? It's linked to it in a big way because the ocean takes up the CO2 that is removed from the atmosphere, and this is where eventually it goes. And the time scales over which this removal mechanism happens is linked to ocean circulation. And ocean circulation is also linked to chemical processes in the oceans, namely the depth at which calcite can form. So this is all highly relevant. And there's another process, and this is biological. The ocean circulation also helps to bring micronutrients into the midst of the oceans, which then helps phytoplankton growth, which again sequesters more carbon. So this is all linked very closely.
Nick, same question. So we'll hear about you and your research on Friday on the origins of life.
Well, I'm sure it is linked very closely, but it's very difficult. I suppose what I get from this is just how complex this system is now and how little we understood about it until very recently. And what I am trying to do is understand the role of the oceans 4 billion years ago in deep-sea hydrothermal vents. Now, I think, not everybody agrees, some people think that life started on land in Darwin's warm pond. I think it started in the oceans. Convection currents and so on are almost certainly absolutely central to the mixing, but also the the moon was a lot closer. There was probably a lot more turbulence. There was probably much less land. I have no idea how these patterns, I mean, I was very struck how sensitive they are to the presence of land and the shape of the land and so on. So if there's much less land, I have no idea really from this what that means for the actual currents and so on. The other thing which is very difficult to constrain is the salinity of the early oceans. Probably the best guess is it was similar to today, but again, the salinity, a lot of the temperatures and the salinity seem to matter a great deal in terms of the mixing and or the failure to mix and the turbulence. So I suppose I'm saying I don't know. These are all themes that are almost certainly extremely important for what I'm working on, but it's very difficult for me to go from the present day. I savor the complexity of the present day, but how I can extrapolate that backwards to 4 billion years ago, I have to say I don't have a clear idea.
Well, maybe, Kim, you do, because you also work on oceans, and we'll hear about you and your research tomorrow on the aerosol. Please.
Yeah, I mean, it's very relevant. I mean, the ocean and the atmosphere talk to each other all the time. And one of the issues is that we need to work together more. You know, basically the ocean, the circulation patterns in the ocean, I've come to appreciate, and how they're changing are actually changing the atmospheric flow patterns as well. And that's a surprise to most people, that the flow of the ocean can control the atmosphere. The other thing the ocean does, as I will talk more about tomorrow in the turbulence, is very interesting to me, because you know, the ocean emits mini aerosols, which I study, which seed clouds, which have a huge effect on climate. The ocean also, through turbulence, emits a lot of gases, just like a forest. And so, again, cloud seeds and climate. And atmospheric composition is really, really strongly controlled by the ocean. So I'm very fascinated. I work with oceanographers all the time, and you'll hear more tomorrow about how we're trying to link the two together more and more.
So I'll go for one additional question to you, Ilker, but also to the three of you. You might know that the decade 21 to 30, so 2021 to 2030, has been named by the UN the decade for the ocean. And the vision for that decade is such: the science we need for the ocean we want. So what is the science we need? What is your biggest wish for the science of the oceans that we need for the ocean we want to have? Maybe start with Ilker and then the others.
Yeah, that's two different questions, what we need and what we want. Yeah? So, of course, I'm passionate about the things I want, but I can't claim that that's really what we need. I know they are useful, like the ocean mixing and turbulence. I hope I convinced you that that matters. So I'd like to do more research, expect more research to get a global coverage of good ocean mixing studies, and have more interdisciplinary studies in relation to air-sea interactions, so atmosphere and ocean talk to each other, and also the links to ecosystem. How all this turbulent mixing, what does it mean for the interactions with the biology and all this nutrient, how that's distributed with all this turbulence? So we have to have interdisciplinary studies, I think.
Comments?
Yeah, I just second everything that he said. I think that the future is all about the integration across the disciplines of the biology and the physics and the chemistry and the atmosphere and the oceans and the land. They all talk. And so we've spent a lot of time understanding each one of our, I call them compartments in the environment. We're all talking about different compartments this week, but I think integrating them is absolutely key. I agree with that.
Any comment? Otherwise, I propose to open the floor for questions. So again, you can ask your questions both in English and French, and there'll be simultaneous translation for the guests on stage. And also, for those of you following up online, you can ask your question by writing in the chat system of the live stream, and they will be relayed. Actually, we already have one question from the online audience.
We have one technical question, which is, you have highlighted the data side of your research, and somebody is asking how much computing power plays a role in what you're doing.
computing role, I guess you are referring to like how to do this numerically, because computing power for analyzing my data, you don't need that much. But to model turbulence, you have to do direct numerical simulations. Technically, that's what it's called. Then we are talking about a tank in a, like a small tank of water. So then you can learn all about, you don't need to parameterize anything. You can learn all about it. And that requires already supercomputers. I'm not a modeler. I don't want to say wrong things. But the next step is the large eddy simulation. Then you resolve quite a lot, the larger eddies, but you don't get all the tiny bits of the turbulence. Then you can represent the oceanic fronts, a bit larger structures, order kilometer, I think. Still using supercomputers. Yeah. So you need a substantial computational power. You can't get anywhere close in regional models or global models.
There's a second question, which relates to actually some of the things we've heard, and that is to know how much volcanic activity in the oceans plays a role in the circulation and in the turbulence.
That's a tough one. Nice question. So I think volcanic activity plays a huge role in local turbulence, but probably not so in the integrated sense, in the global sense. I know, for example, the geothermal heating on global average is only 0.05 watts per square meter, so very negligible net flux from that. But what was the second part of the question?
The question was to know whether this volcanic activity influences also the turbulence, and whether that can have a macroscopic effect.
I guess so. I don't know.
Probably not. Good to hear that sometimes. I don't know. Yeah.
Might I ask a question myself that kind of relates to that? Because I'm thinking about the end Permian extinction, where the Siberian traps were flowing lava across large areas, and it's linked with global warming. I don't know how strong, it's not what I work on, but I don't know how strong these ideas are, but the oceans becoming anoxic, becoming sulfidic, so saturated with hydrogen sulfide, and a mass extinction, the largest mass extinction in the history of the Earth. And I have the feeling, but I don't know if this is really true, that the warmer the oceans, the less you have the mixing and the currents in the way. I certainly had that impression from some of your images.
Mm-hmm. So I guess if you don't have turbulent mixing for some reason, you come to a stage that you just keep on filling the basin from the bottom with cold water, and you have the radiation from the top. And you end up with a very thin layer of very warm water and a very strong stratification, funny ocean, unnatural. But probably in the old days, many years ago, that the tides were so different and the water levels so different that you could still force some tidal induced mixing and generate the power you need to maintain some circulation. But these are all dark ages for me, sorry.
Are there questions in the audience? Did I see a question there? No, that's not the case. So I have many questions, actually. You have a question, great.
Yeah, Ilker. So how well do we actually know deep water circulation? As far as I understood, the floaters you've shown to us, the pictures, they float on the surface of the ocean, correct? Mm-hmm. But they don't measure deep water, so they measure surface turbulence. But how well and at what resolution can we measure the velocity of water at depth, and how's that done? Mm. Or did I miss that part?
No, I haven't really gone into that. But one thing is those Argo floats. They are ballasted for 1,000 meters depth, okay. So they drift for 10 days, and between each surfacing points, then you get a over 10 days, you get an estimate of the mean ocean current at 1,000 meters. So that's, I don't know if that's deep enough for you, but that gives a good indication of the deep circulation. And they are all over the world ocean, so they provide good data. Other than that, we have more instruments. We identify some gateways, some important regions where exchange occurs, where important circulations happen. Then we deploy moorings. These are bottom-anchored lines to which we attach different instruments to measure the ocean currents. They can profile the ocean currents, and we get good insight onto the volume transport rates and the currents from those. There's been global programs, international collaborations to capture those at different gateways.
So can we detect whether the Northern Atlantic thermohaline circulation is slowing down or not?
May I add on that and ask you if the titles that we sometimes see in the media of this heat conveyor belt that would stop is pure hype from the media, or is it something that could happen?
Yeah, there are many answers to that. So it won't stop. I can assure you, yeah, it won't stop. If you look at, for example, the IPCC report, they would claim with relatively high confidence that there may be some slowing down, but it won't stop. There's no data suggesting that. So we measure, actually, since 2004, I think, we measure the meridional overturning circulation, Atlantic part of that, at an array called Rapid Array, all the way from the Florida Strait to the other side of the Atlantic Ocean. So that covers the entire circulation at that latitude, 26 degrees north. So with that, we can actually look at the data available, I think 14 years or so far. It doesn't show a significant trend of slowing down. It shows a hint of slowing down. So there's some suggestion of some reduction in the strength of the overturning circulation. But it's not highly confident yet. Of our backyard in Norway, we've been maintaining an array looking at the strength of the Gulf Stream, our version of the Gulf Stream, for 25 years. That hasn't shown any indications of reduction in strength. So we are not there yet in terms of length of observations to make any conclusions.
Are there questions in the room? Yes, there is one. Please, the microphone.
Thank you so much for your very interesting conference. You were talking about the density of the water, and I did not understand correctly this term. Is it connected with the heat? I mean, cold water is more dense than warm water. Is that what you meant, or something else?
Yeah, good question. Sorry, I was not clear on many technical details. So the ocean density, it's dependent on temperature, salinity, and the pressure. Higher temperature is lighter water. Higher salinity is denser water. That's why if you freeze sea ice, you eject salt so that becomes dense, so it will sink. Or at high latitudes, if you lose heat to atmosphere, you cool the surface, that will be colder, denser, it will sink. And also it increases with pressure, but that's not dynamically important. We remove that effect.
There's another question right at the top there.
Oui, bonsoir. J'ai une question sur la salinité de l'eau. Est-ce que ça a une importance sur les mers, sur les poissons, sur nous, je ne sais pas. Est-ce qu'en augmentant la température, ça augmente la salinité?
Oh, thank you. That's a good question. It's a complicated one, but I don't think you want to go there. That's something we call spice in the ocean. The temperature and salinity is spicy ocean. Is that you can have the same density, you can increase the temperature, reduce the salinity, then you can end up at the same density, or vice versa. So some changes in temperature can be compensated by changes in salinity, and that has consequences for how the waters are then distributed and circulated. But per se, a change in temperature does not translate to anything like one-to-one link to salinity changes. So, but there may be regions and times that may occur, but that's a different process. So there are two different things normally. And for the
that was
the
it.
question,
About
was
the salinity. Is there another? Yeah, there's one here. Mike's coming.
It's linked to the same question with the increasing of the pollution of the oceans with microplastics and wastewater and different waters we send and the increase in the oceans. How can you imagine the impact of the currents and maybe the chemistry of the oceans?
Yeah, so that's a good one too, thank you. So of course, turbulence is very important for the distribution of microplastics in the ocean, but also the mean circulation patterns, the eddies, maybe all the scales and their interactions, like I tried to motivate you in the beginning, that their interactions must be understood properly to sufficiently model the distribution of the microplastics. I think my colleagues are doing modeling studies. It's very difficult to measure microplastic concentration, so you have to rely on the distribution from model fields. So they can come a good way to track where the different concentrations are going. But my understanding is that turbulent mixing is of huge importance for the whole process. I hope the technology comes where we can measure microplastic concentration properly. I'm not into that literature, but I don't think it's very practical yet.
Maybe Kim, you want to comment on that?
Yeah, I mean, as far as the microplastic issue, and also the wastewater is hugely important in coastal regions, especially. And we are looking at this right now, especially, but more from the standpoint of the aerosolization. But from the microplastics, it does seem like the currents will, that's how you get them concentrated in the gyres and that kind of thing. But they are getting better at if you collect the water, you can stain and count microplastics now. It's getting much, much better. But in the air, we're still trying to figure out whether they're important.
Is there another question in the room? Otherwise, I do have one actually. It's not similar, but talking about pollution, about microplastics, it's about protection of the oceans, right? So I would like to take you on another level, also related to this UN decade of the oceans. The topic obviously belongs to the so-called science of the commons being the things that belong to no one or everybody or humanity, if we can say that. An article in the scientific literature last month proposed to consider the oceans as a living entity by itself and to protect this as a living entity. So in terms of governance, in terms of protection, what is your view on what needs to be done and by whom?
Yeah, thank you. So, you know what, the marine protected areas, such a low percentage of the global ocean coverage, it's a very small percentage, I don't know the number, but the experience is that each time they protect an area, it flourishes. It's the species grow, it's a healthy environment, not only for the ecosystem in there, but also for humans around. So I totally agree. We have to increase the area of marine protected areas, so that we are not there yet. And there's good experience that when we do that, things change. So I think that can only be done at a political level. So different nations have to act on the political side.
Do we have the right governance tool to do that? I don't know if some of you want to comment. If you, Kim.
You know, I'm thinking like from the ocean perspective, who is responsible? You know, it's always who's responsible, who owns it, who cares? You know, how can you? Who is? Do you know? It is a tough one. I mean, air quality I can answer. The air quality is like the state above which it exists in the federal government and the different governments. But oceans, it's like people always seem to point at it being someone else, a lot of times someone else's problem, right?
Mm-hmm. Yeah, unfortunately, each country has a very limited part of the ocean. A certain nautical miles is their economic zone that they rule over. So otherwise than the international law of the seas that rule. And so it's very difficult to make decisions that hold all over the place because there are so many voices. And so it's not well governed, I think. So there's some action to be done.
Yeah, you mentioned the law of the sea, which exists, and as far as I know, this is a legal framework that rules like shipment and where are you allowed to fish and which part of the shelf area belongs to country and these things, and maybe even a bit of deep sea mining. But if we want to do like these new methods that we've spoken about in the first talk about like this geoengineering thing where even the ocean, like putting alkalinity into the oceans or micronutrients to sequester CO2 or other things we want to do with the oceans, there's absolutely no legal framework under which one can do this, which is a huge problem because the question is who's allowed to do this, who has the responsibility if something goes wrong, who has the benefit, who pays, and so the oceans are not legally ruled. So even if it would be technically possible, legally it would not be possible. It's a big problem. And the way the big of the countries in the world are set up at the moment, as we all know, it doesn't look as if such a framework will come about very soon.
Nick, about this idea of considering the oceans as a living entity, you're a life expert and you like fluxes.
I mean, that's words, I would say. I mean, the oceans are enormously precious, whether you want to call them living or not living. I don't think it makes any difference to me, personally. The thing is, I mean, we're back to governance, and I just, you know, this is where I really do despair, because I don't know what we do. It's obvious that we have to form some functional, effective global governance, not just for the oceans, but for pretty much everything that's going wrong. And we need to do it now. And there just doesn't seem to be a political way of making it happen. So I think scientifically, we can solve many of these problems. It's just that politically, it seems so far away. And yet, at the same time, the reason that I have some optimism is that I sense that the majority of people, and a very strong majority of young people, feel very strongly about these issues and are politically more active, not necessarily in terms of voting, but in terms of activism. I hope voting too. But I think there needs to be a worldwide movement of people who care. And that's the only source of real optimism that I have, because I think we are globally, the young especially, beginning to talk a common language, beginning to recognize that this is a global threat, and that, you know, I think for it to work, we're talking about, I hesitate to use the word revolution, but we really have to overturn a lot of the way that the current systems are working. That's not an anti-capitalist diatribe or anything. It's simply that the way it works now is not compatible with a long-term future for humanity. And we urgently need to fix global governance in a way that works for the majority of people.
That could be the conclusion, unless you want to add something. No, that's for sure. If there is one last question there. I'll take it and then we'll close the evening.
Alors, j'ai même deux petites questions. Donc, en fait, sur ce qu'on vient de dire, j'ai entendu qu'il y a des gens qui proposent de donner des noms d'humains à la nature pour qu'on la protège plus. Alors, je ne sais pas si ça peut être une solution ou un début de solution ou pas du tout. Et puis, la deuxième, c'est juste pour en revenir au volcan de hier. Et c'est par rapport au volcan sous-marin. Est-ce que ce serait possible qu'un volcan sous-marin surgisse comme ça? Voilà, c'est tout.
So, on a déjà répondu quelque part à la question des volcans et de leur impact tout à l'heure. Donc, on the first part of the question, so really considering oceans like a living entity, it's not really giving names or human names, but really considering the ocean as a living entity. You want to react to what maybe Nick said, and that could be the conclusion of the evening, Ilker.
Yeah, I mean, in a way, I agree with Nick that it doesn't matter if it's living or not. It's very important. It's hugely important for the climate system, for the humans. It provides us everything we need. But I see the benefit of thinking as it's more fragile, it's living. Maybe there's a merit to it that we can protect it better if we agree that it's a living ecosystem, which it is actually. But yeah, I'd like to think it that way. So let's keep it alive.
So thank you very much. Do you want to add something? Yeah, please do. Last word.
Well, I mean, I suppose the idea of Gaia is something that goes back much further, and it's something that a lot of people have sympathy with the idea, even if I don't think the planet is living as such, but Gaia is a very pleasing idea, and the oceans fit into that context. Yeah. Just one other final point, if I may, in terms of use of words or definitions. We really, there are various people who have tried to put value on things, and this is slightly linked. Calling the ocean living is putting some kind of valuation on it. And a serious problem with economics at the moment is that it doesn't value the resources of the planet. And that includes biodiversity and so on. It includes the rainforests and everything else. And until it's painful for a lot of people to commoditize nature. But at the moment, economics is working in the opposite, is pulling in the opposite direction. And we need to find a way of valuing things in a way that makes sense.
I think that's a nice conclusion. A big round of applause for Ilker Fer and guests tonight. Voilà. Il me reste 3 informations à vous donner. La première, c'est que demain, on aura le plaisir d'entendre Kim Pracer sur les aérosols. La deuxième information, mais vous le savez maintenant, il y a des animations tous les jours, encore demain et après-demain, avant le colloque du soir, entre 5h30 et 6h30 devant, par l'équipe du Sciencescope avec des expériences scientifiques de vulgarisation. Et la dernière information, c'est toujours la tenue du spectacle Son et Lumière, cette année au musée d'art et d'histoire, pas au Parc des Bastions, au musée d'art et d'histoire, 3 fois à 6h30, 7h30 et 8h30, ça dure 20 minutes. Il paraît que c'est fantastique, je n'ai pas encore eu l'occasion d'aller le voir, mais allez-y, vous ne serez certainement pas déçus. Voilà, je vous souhaite une très bonne soirée et je vous donne rendez-vous à demain ou après-demain pour ceux qui peuvent. Bonne soirée, merci.